Good afternoon. NASA told me to pass the time away to Mars, that I could give a little introduction on the atomic theory and all of its aspects. Now, you are wondering what the atomic theory is, of course, and that is why I have this video to explain it to you. But to understand the atomic theory, we have to go back all the way to the Grecian times, around 400 BC, with the Grecian thinker Democritus. Now, Democritus composed a theory that basically said that all things are composed of tiny indivisible things called atoms, the word atom comes from the Greek word that essentially means indivisible, which we will find is somewhat correct, but will be revised over many centuries. A fellow Grecian thinker, Aristotle, did not believe in such a theory, and his opinion was the common way of thinking for almost 2,000 years. It wasn't until the late 18th century when chemists were able to discover that, in fact, atoms were almost impossibly broken down by ordinary means. Through experiments conducted in the 1790s through the 1800s, three basic laws were created to describe atoms and their properties. First was the law of conservation of mass, which states that in chemical reactions, the mass of the beginning elements that are either combined or fissioned, the resulting substances will have the same mass, although maybe in a different form, of course. The second law is the law of definite proportions, which says for any substance with two or more elements, no matter what size of the sample, the proportions of those elements within the substance will always remain the same. For example, normal table salt, which is sodium chloride, will always contain 39.34% sodium and 60.66% chlorine. No matter what size, they will always come to that proportion. The third law is the law of multiple proportions, which is probably the most tricky one to understand. But the law of multiple proportions states that for compounds that can be composed of the same two elements, like multiple compounds, the proportions between those two elements will remain the same. The easiest way to explain this is the relationship between oxygen and carbon. They can form carbon monoxide or carbon dioxide. Now, in carbon monoxide, the ratio is there is 1 gram of carbon to every 1.33 oxygen. At the same time, however, for carbon dioxide, there is 1 gram of carbon for every 2.66 oxygen. So the ratio between carbon and oxygen in the relative compounds are 2 to 1. So these chemists have come to these conclusions, but in 1808, a scientist by the name of John Dalton was looking for an explanation to these laws and possibly some other properties of these atoms. All of his findings can be rounded out to a couple of ideas. The first being the one that was established back in 400 BC, that all matter is composed of things called atoms, which still holds true till today. The next being all atoms of an element are identical in size and physical properties, and that atoms of different elements are of different size and different properties, which we'll talk to how correct that was. The next, which the first part of it was proven wrong, was that they cannot be subdivided, created, or destroyed. We still established that they cannot be created or destroyed, but they can be subdivided through special reactions. And the fourth one, which goes along with the law of multiple proportions, say that atoms of different elements can combine to form whole number ratios to each other in different compounds, which is what we talked about with carbon and oxygen. And the last one, which we know, is that chemical reactions combine atoms. And the last one we all know is that chemical reactions combine, rearrange, or separate atoms. The other part of Dalton's theory which proved incorrect was that all atoms of a given element are of the same size and mass. This is not true, however, because of isotopes, which we will discuss later on. So now that we had established what atoms were all about, now we had to know what composed of these atoms and what we could do with them. One of the first experiments was by a man named Joseph John Thomson, who created the cathode ray experiment. Now in the cathode ray experiment, a cathode ray was put against a power source with one negative end and one positive end. The particles in it shot out from the negative end and were pushed away, but attracted to the positive end. Now, when an outside magnet was placed near with the positive end towards it, the particles were more tuned towards that than the positive, which was connected to the cathode ray. This led scientists to realize that these particles were negatively charged. This would be the electron. But the discovery of the electron now led to a greater understanding of atoms. They understood that electrons did not have much mass, so the rest of the atom must have particles of a greater mass. Also, since there was an electric charge, and the atoms we were studying were neutral, there had to be a positive charge to counteract them. This would become the protons of the atom. Another part of the electron that had to be solved out was how much charge the electron had and how much it weighed. In 1909, Robert A. Milliken was conducting an experiment to figure out exactly how much charge the electron had and how much mass it contained. We already knew it had a large charge to mass ratio, but we're all about exact numbers here in the future, so that's why we continue to study it. Based on how much charge I figured out it had, they determined that the electron is about 1/2000th the size of a hydrogen atom, which is the smallest atom known to man. As we continued on, we figured out that the electron actually has a mass of 9.109 times 10 to the negative 31 kilograms, which actually ended up being 1,837th the size of a hydrogen atom. So it is incredible how far we have come and how close they actually were with the far less advanced tools that they had to study these electrons. Next, I'm going to talk to you about Ernest Rutherford experiment with gold foil. Wait a second, what's wrong with the recording? What's going on? Hey, the picture back. What's going on? Hello? Is this thing on? Oh, I don't know what these darn things are. Well, howdy there, partner. My name's Tex. Some guy said he was from the future and pulled me into the little box or whatever and told me that he's telling me to pay me £1 of gold to talk about what I'm about to talk about. Said he'd get a mighty good laugh out of it. I do enjoy making people laugh. May not be me this time. And what I get to talk about gold, so I figured it'd be fun. Can't hurt. So what I'm supposed to talk to you about is something called nuclear random chemistry or something like that. I'm supposed to talk about some guy named some guy named Ernest Rutherford from this place called New Zealand. I've never heard of New Zealand, but apparently this guy has. Now what this here Rutherford guy did, took a piece of gold foil, and what he did, he shot these things called alpha particles. Like I said, folks, I have no idea what I'm talking about, but I'm doing this for gold. Now, he shot these alpha particles at this gold. Well, get this. It went straight through, like nothing ever hit it. But it did bounce around a little bit and hit this little sheet around that held the particles. I don't know. The only particles I know are the dust that kicks up my eyes every time I ride my horse, buckaroo. So I don't know. Now, apparently they didn't want anyone knowing this, but when they shot through every now and then, it bounced right back like nothing even happened. I don't know. I don't know, folks. I say it's like shooting a bullet at a piece of tissue paper and it coming right back and hits you square in the face. I'd hate if that happened. Luckily, I don't shoot a tissue paper for a living. Now, what they say this all means is that something called an atom has this thing called nucleus. Kind of sounds like that word nuclear, but I don't know. And because it had this nucleus, it must have been real small, but it must have hit something real small on that piece of gold foil too, and it bounced right back. But most of it just went through, and it bounced off. Well, apparently that's all I'm supposed to talk about. And the guy behind the camera is really shaking his head and wanted me to stop. But I'd like to say, I want you all to have a nice day, folks. And I hope I get to go back and run my horse some more. I want to enjoy that pound of gold at the gambling place. Yeehaw! Alright, well, I have no idea what just happened, folks. But on the playback, we realized that this intruder seemed to have somehow accurately described what Ernest Rutherford's discovery of gold foil was. I guess we should not waste any more time and continue on with our lesson. So now that Rutherford had understood that there was a nucleus of the atom, now it was time for us to study the innermost part of the atom, and the part with the most mass. We have electrons, which orbit in a cloud formation around the nucleus. And within the nucleus, we have two different subatomic particles. One is a proton, which carries the positive charge to counteract the negative charge of electrons, and we have the neutrons, which also contribute to the mass of the atom. After figuring out that atoms of different elements have a different level of positive charge, we now had an easy way to determine which atoms were which with the number of protons that they contained. Therefore, the proton is directly related to the atomic number, which you will find on the periodic table, which we will continue going into more detail about as this lesson progresses. Atoms begin from the most common form of hydrogen, which is just one proton and one neutron attached with a single electron floating around it, which is our smallest stable atom. Now, as we all understand magnets, two positive ends together and two negative ends together will immediately repel each other, sometimes violently depending on the strength of the magnet. However, despite having a positive charge, this is not exactly true for protons. Protons, when extremely close together, actually form a very strong bond. Now, however, this only goes up until about 83 protons together. Until then, it becomes much more unstable. Of course, we have many elements above 83, the atomic number of 83. So we have a lot of unstable elements that we know of. This doesn't make them completely unusable, but it makes them a lot harder to work with and a lot less safe. When we were discussing the debunking of parts of Dalton's otherwise sound atomic theory, we discussed that isotopes disprove this statement that atoms of the same element all are of the exact same size and mass. An atom can have a different number of neutrons, which both change its mass and create what is an isotope, which is merely just an element that has a different number of neutrons. Just as having too many protons creates an unstable atom, so does having too many neutrons compared to the protons. The ratio between protons and neutrons can only go up to about 1.5 neutrons for every one proton. This means that less common variations of the hydrogen atom, more like hydrogen 4 and hydrogen 5, are considerably less stable because the ratio is far higher than 1.5 to 1. These variations create a difference in the mass number, which is the decimal that you find at the bottom of each periodic box that describes each element. The reason the mass number is not an exactly whole number is because the varying masses create a different average. Now, this average is not the same kind of average you calculate in your math class or normal everyday life. The mass number is actually determined by the abundance of the isotope, not just the actual mass of each isotope. So, for instance, if you were dealing with 3 isotopes and you had 50 of the atom with 1 neutron, 25 of the atom with 2 neutrons, and 25 of the atom with 3 neutrons, when you calculate it out, it's an odd concept, but the math itself is sound. Now that we know what the atomic number and the mass number is, it will be much easier to identify in our entire periodic table block. Now behind me you will see an example of an entire periodic block. This one being of tungsten. Now first we have the atomic number on top, which is 74, meaning it is generally a stable element, and it also has 74 protons. And below its name, you will see that it has a mass number of 183.84. Now, the big letter we haven't discussed yet is the element symbol. Each element has a symbol to easier identify it in chemical reaction equations. This one, you might be wondering why, is a W. The original name of tungsten was actually wolfram, so they chose the W as its element symbol. When they changed the name, they didn't want to change the symbol for easier understanding of older reactions. And not every element symbol has to do with the first 2 letters, or the first 1 or 2 letters of its element name. For example, you would think platinum would be PL. However, its element symbol is actually PT. Well, that was our lesson, and I hope you would... Oh, come on, it's happening again. Come on, we're almost done here. Come on. Come on, you stupid thing. Even in the future, nothing works. I thought I'd never see you folks again. Well, I'm glad you got to see me again. Wanted to say hi. I am enjoying that gold. They didn't let me spend it, though. The guy said he wanted to do another laugh. He was laughing so hard when he stopped hitting that record button or whatever he said. Well, like I said, I want you all to have a nice day, and I hope you have learned more to expand your knowledge. I don't know, something scrolling past called a teleprompter. Kind of looks like a telegraph. I don't know why how it's moving though. It must be that magic effects tricking my eyes again. I need to stop hitting that bar too late at night. Well, like I said, folks, hope you have a nice day.
With silence.